Hello guys, I'm here again today to present you a new lecture about cell movement and external force. Let me remind you that this workshop is live streamed and it's being recorded to be distributed after all. Okay, let's start. Here is the outline of the presentation, the lecture. I will give you a very brief introduction about single-cell migration, and what is the persistent time in single-cell migration, how to implement it in the CompuCell, and how do we produce forces over the cells to make it then migrate. That is a functionality of CompuCell, which is built in the external potential plugin that I will describe later. To use this plugin, I need to give you a word about periodic boundary conditions, again, just to reinforce what you probably already know. Then I will include in the presentation actually 3 exercises. If I have time, I will present the 4th one, about how to make simulations with applied cells in a single cells. After that, at the beginning, the single cell will be just the cell as we have seen so far, a single blob in the middle of the grid. And the second exercise, I will try to make our cell more realistic. I mean, including in the cell 3 components, which I will show you later. After, I try to make the same cell in a 3D environment, a 3D cell, not a 2D cell like we have seen so far. And finally, because some people during the presentations asked for flowing cells, multiple cells flowing in a channel, I included here a small exercise, a demo, to show how to produce such a flowing cells in a channel. Okay, and finally the well-known questionnaire. Let's start. One of those big questions we have in biology is how do the living cells migrate, even either isolated or collectively, like a tissue's motion. Okay, and we have many processes in biology where this migration of cells are present. We can start from the beginning of life, the embryonic development. Here you have a simple picture showing the stage of gastrulation in sea urchin, and you can see the phases or the cells moving around and produce this invagination of the egg. That will be produced the spinal cord and so on. It's a very beginning steps of the embryonic development. We can find also cell movement in wound healing. If you have a scar, well, the tissue is broken in a site of your body, then cells start to migrate to this region to close the wound and finally get it fixed. Of course, the fixed pattern at the end is not well done because we have scars, and the scars is a product of some extra proliferation of cells in the intermediate phase of the process as a whole. Also, we have the inflammatory response for when your body is attacked for some virus. We have now for this bad times having COVID, and it was a complicated task to find how the virus install and replicate itself inside our organism. This is a very important process to know to be able to build vaccines. And finally, but last but not lastly, we have the phenomenon of the metastasis in cancer pathology. See, we have the blood of cancer cells here. Those cells perforate the blood, a blood vessel, penetrates in the blood vessel, and it moves around your body, get out of the vein, and establish a secondary tumor elsewhere. So this is the worst part of the cancer disease. Anyway, so the question, how does a cell move? Well, a single cell can present different kind of mechanisms to migrate. First, we have the external mechanism. We can see here these motions of an spermatozoid, which moves with a flagella mechanism. And this side we have a paramecium, which moves with cilia mechanism. Okay. Another kind of mechanisms are the internal mechanisms. We have here the lobopodial motion, where there is pressure difference inside the cell, which produces the front of the cell, and the cells go to that direction, being pulled by the actin fibers inside the cell. The nucleus go later, see. We have also the amoeboid motion here, as the cell moves like a whole thing. And finally, we have the lamellipodial motion, which is in this movie. See, the lamellipodial part here is quite hard to see because it's a very thin structure in the front of the cell. Okay, this lamellipodial motion is the one we are focusing in this presentation here. So let me describe a little bit about how the lamellipodium is formed. First, we have to understand the following behaviors, different behaviors for a cell while it is moving. We can have at least three kinds of different motions. See, the first one, well, the movie is too fast. Let me start over here. Is the diffusion motion. The cell doesn't go anywhere. After that, the cell can move a little bit, and it produces some long way during the motion. This is the persistent way. And finally, it's a combination of both. The cell randomly moves around a certain point, persistent moves to another position, and randomly moves in that new position. Okay, those are the three kinds of movements we can see with lamellipodium cell motion. The machinery to produce this kind of motion, which is the lamellipodium. The lamellipodium is this part here, where you can see a schematic showing that very complicated mesh of actin and stress fibers in the cells. In this picture down here, we can see an image where this machinery is showed with different parts of the lamellipodium. The very front part here in the red part, and the green part is where the fiber stress start to form and go to connect to cytoskeleton of the cell. At the front part here, we have some actin monomers that stick to each other to form these fibers. Here, the actin monomer, which is floating in the cytoplasm, moves to the tip of the cell, connected to the fiber, pull the cell forward here in this direction, and the rear part of this small fiber here, the actin monomers are detached and go to the tip part. You know, you have a constant number of actin monomers. They have to be reused from the end to the tip, from the rear part to the front part. Okay, this is a kind of treadmill motion of the actin monomers. In this small move here, this is a quick move here, you can see the formation of the tip fibers according with the motion of the actin monomers. See? Oops. Okay, so we should be able to reproduce this. This is a very, very complicated thing. It's a subcellular process. We have to try to minimize this. Before to start to do that, let's talk a little bit about the persistence time. Why the cell presents the persistent time? Well, again, to be able to move, the cell needs to create a lamellipodium, and that lamellipodium has a lifetime of 30 seconds around that for a cell. So during this time, the cell goes where the lamellipodium is formed. So at least 30 seconds, the cell moves in that direction. This 30 seconds of moving in the direction of the lamellipodium is the persistent time. So for some reason, the cell stops at the next position. For environmental reasons, maybe the cell rearrange the actin monomers inside the cytoplasm and start to form the lamellipodium in another direction. And the cell goes to this new direction. That is what we call persistent random walk. Why? Because if you take a window time where you are seeing the persistent time, you see a persistent movement. The cell goes from here to here, to the end of the file. But if you took a great picture, a movie, for example, when you can see all the changes of motion during this big of time window, you have a random walk for the cell. He moves here, goes there, moves there, moves there, moves there, and so on. Okay? This is, I think, this random motion CompuCell3D has by default. You have seen so far when you create the cells keep ruffling, the membrane keep ruffling all the time. So if you make a track of the center of mass of those cells that we have created so far, the center of mass will be executing a random walk. I mean, it's not going anywhere, just moving around some equilibrium position. Okay, but we needed then to implement the persist time over the cell to have the combination of both the persistent random walk. Let's see how to do it. Okay, the simplest way to implement this persistent time is by forcing the cell to move in a given direction. And this forcing will be act for a certain amount of time that you define how much it should be, which will be this persistent time. So the cell moves for a persistent time you define, stops for example, to suffer the force, to be acted by an external force, and then moves again to another place if the forces changes its direction. Okay, let's see how. Okay, this is a little bit of physics now. We know that CompuCell works with variations of energy. All the terms you have included so far in the system to make the cells exist, like contact and volume and surface, are energy terms. When you have energy terms, if you have variation of energy of those terms, you produce force. So you can say that if we produce force, to produce force, we have to, for example, to produce a variation in the energy, we have to make a force act over the cell to make the cell to displace over a certain amount of space. Okay? Now, in this equation here, it's, I don't know if you are familiar to most of you, I will explain. F is the intensity of the force, the magnitude of the applied force on the cell. This small n with a hat over it means represents a vector, a unitary vector that points the direction where this force is being applied to. Okay, the point between the dot between the first term and the second term is the scalar product. Why do we have the scalar product? Because this term is a vector term, this term is a vector term, and energy is not a vector term. So we have to produce a scalar term from two vectors, and that is achieved by multiplying then with a mathematical tool that is the scalar product. And finally, the delta X is the resulting displacement after the applied force is acting for a certain amount of time. Okay, let's try to understand this in the code. Again, so how do we implement the external potential? This way. The external potential is some constraint which represents the applied force that will make the cell moves from where the cell is to where she wants to go. This is the displacement of the cell. So the cell is in a certain point here, goes there by acting a force over it. So this is the expression for the external potential plugin. However, since both quantities as vectors, you need we need scalar terms in our energy terms, we have to calculate this separately, one by one. I mean, we have to divide the external potential as a contribution of the action of the force in each direction of our system. Let me try to show you this here. You have at the right side here our Cartesian system X, Y, and Z. And the green thing is the cell. The force is being applied in a certain direction here. Okay? Well, as we can decompose this force in each direction of this system, this 3D system. So when we do that, we have a component force acting in the X direction, a component of the force acting in the Y direction, and a component force in the Z direction. And the total energy variation is the sum of all the variations in each direction. I think if you don't understand, we can ask later, please. Anyway, another thing you have to take into account is this minus signal here. If you want to cell to move towards the X positive direction, you have to apply a negative energy in the x direction. This is the origin of the x, the minus sinus in the sinus in this expression. Okay, well, let's see the implementation. But before that, let me talk about periodic boundary conditions. Okay, we are going to represent a cell in a plane like this. But see, if you want to observe our cell as much as we want, we cannot confine the cell in this region here. We have to think about a cell moving in an infinite plane. But how do we cannot implement an infinite plane in CompCell? It requires infinite memory. So you use the technique of periodic boundary conditions. What does that mean? That means that we are going to make the y boundary here, the lower y boundary here, to be connected with this upper boundary here. And the x boundary to the right side to be connected with the left bound. So what we are going to create here is this. Look, it's a small movie, it's less than 1 minute. This is a topological transformation. You have the plane. So you are making the y boundaries connected and the x boundary connect. So now you don't have a plane anymore. You have a torus. And over this torus, the cell will move forever. So we have a kind of infinite plane here, representing this fixed region here, this small region here. Okay? I hope you have now more clear what is the meaning of the periodic boundary conditions. Pedro has showed last, I think yesterday or the day before yesterday, that asteroid game, when you can see the asteroids and the spaceship moving from one boundary and appear in the other boundary. This is why, because the spaceship and the rockets and the meteors are moving on the surface of a torus. Okay, let's go there. So, exercise. Let's do the following. This is the first implementation. I should mention that all these codes are the demos exercise are available to you in the demo parts folders of the student material in the module 4.2. You can download it, open, and each exercise is being divided in 3 steps, 1, 2, and 3. And then you have 4.2.1, 4.2.2, and 4.2.3 in the exercise. I'm going to do in only one. Let me push this here and open to edit and start to build this first one exercise. New project, call E41. Next. Okay, we have a single cell, 10 by 10, it's here, in a 256 box, it's here. But now I'm going to use the periodical boundary conditions for both dimensions, x and y. And it doesn't matter if I use a rectangular slab or a blob initializer to create the cell. Let's stay there. And I'm going to create a moving cell. Okay. So advance, no fields. We have a not fields for today. Contact, volume effects. And now this is the new plugin, external potential local flex. We don't want to keep track of neighbors. Here it is, the code. Okay. I go here, see. The first thing is to fix the cell in some position. We want a 10 by 10 cell, so let's put here 10. And mostly in the middle of the grid, 120, 120, 129, 129. And in the steppables, I will include in the start function the attributes of the cell, which are here, they must be here. I will run over the cells for cell in self.cell list. I say cell dot target volume equals to 100. Cell dot lambda equals to 10. Oh, I must use a bigger cell to see 10. And now I will include the components of the force according to that equation I showed you before. So I have to include cell dot lambda vac x as a component of the force in the x direction as a negative value, 20, and the same. Don't need to be the same value, but for now, let's use the same. Y component in the of the force. Okay, that's it. Then you have your external force applied to the cell. Let's see if it works. See, here is the cell move. I put both components as equals to have the cell moving in the diagonal of the square grid. And now you see, here the cell is changing there, disappear at the extremity of the grid, the upper right extremity of the grid, and appearing in the lower left position. Okay, this is a applied force. This is a constant motion. This is Aristotelic motion. So let's go on. Okay, now we have to we want to accelerate the cell. I think it means that we have to change the force with time. Let's do this the following way. If you want to change the value of the force at a certain amount of time, we need to say to the code and how much is this amount of time. So I'm going to insert here at the beginning of the simulation our time interval as 100. What does that mean? That means that each 100 Monte Carlo step, I will change the value of the applied force, the components of the applied force. And where do I do that? Well, as usual, in the steppable part of excuse me, in the step part of the steppable. So I'm going to copy these two lines here and insert here. And I will change here doing the following. I will test if I am in the right moment to change the velocity or the force, and say if MCS divided by time interval is equal to 0, then I change. So this operation here gives you the rest of the division between MCS and time interval. That means when the rest of the division is 0, then I will change the value of the components, and I will use another quantity here, which depends of the Monte Carlo step that the simulation is. I can do that. Same here. Oops. Understood? So save it and open the simulation. The simulation starts. The cell is there. Mainly, well, that's what we see. It starts with no motion at all. Then after each time interval, the applied force changes and the cell starts to move faster. It's hard to see, but we are going to improve the visualization of this mechanism. Again, the cell disappeared there and appears here. So let's improve this thing. Okay. How? Let's include now a graph plot to see how the speed, the resulting speed of the cell, appears in a graph. Now I need a little more equations here, I know, but it's equations calculated velocity, which is displacement over time. So I think everybody knows that, I hope. Again, since we are going to show in a graph the speed of the cell, we need to calculate the magnitude of the velocity. Since velocity is a vector quantity, we need to calculate the components of this velocity quantity, which are the velocity in the x direction and the velocity in the y direction. And after that, to calculate the modulus like this square root of this expression here. The same applies for the applied force. If you want to know the intensity, the magnitude of the total applied force, you have to make the same operation of that and sum the square of the components and extract the square root of the sum. This is physics 101, I think. Okay. Anyway, let's implement that. But okay, look here. We need to know, to calculate the displacement, the position of the center of mass of the cell in two different positions, two different times, actually. The old one and the next one, where the cell was and where the cell goes. Okay. Now we have to implement to a new entry into cell dictionary to store the previous position of the center of mass. Because the CompuCell gives you the actual position. But since we are not going to see in the time in the Monte Carlo step immediately before, and we need to know where the cell was in some Monte Carlo step before. So I will include here a dictionary like old X center of mass in the start function, of course, because this is the first time I'm run the code. And this start function, the old center of mass is the initial position of the cell. So is this the actual X center of mass. The same, I have to have another dictionary for the Y component of center of mass. That is, okay? Now I want to see the things. So I need our, where is that? Here. Graph window, the plot window, and put here is speed versus force. The force will be the axis, the x-axis. By force mean I'm saying that the modulus, the magnitude of the force. And here, the magnitude of the velocity. And I will call this speed or speed. Don't need this one. Okay, so we have this start function done. So I have to calculate the speed. This is a thing we have to do based on the previous slide where we defined the velocity components. So let's go. Maybe I should copy this from to not lose much time. Let's see where it is. I think it's here. Yeah. I will copy from the version you have, guys. Yeah, I will explain everything, okay? Control. copy. I have to include this here. If it is time to change, I will change the values. I will calculate the speed and the force this way. See, in this line, I'm calculate the displacement, the actual position of the center of mass minus the old one. You know, this position here is the position at this Monte Carlo step here. And this one is the position at the beginning of the simulation. So we have a displacement of about 100 Monte Carlo steps here. Okay? Now I need something. Since we are calculating a quantity here, we have to check if this displacement is moving a cell from the end of the grid through teleportation, if you want, to the beginning of the grid of the left side, for example. I mean, the question is, do the cell cross the boundary at this point? If the cell cross the boundary, we have to adjust the displacement. Because, you know, you have a cell moving from x equals to 500, for example, to 1 to the other side, if it goes to the right side. So you have to correct that. This correction is made in with this line here. If the modulus of the dx is bigger than half of the grid, so the cell has crossed a boundary, either the left one or the right one. So we correct that by putting the cell in the right position. I mean, the displacement in the right one. We decrease the displacement for the length of the grid in the x direction. So we calculate the axis in this way. The same thing we do for the y displacement. Cell y minus cell out. Calculated, test if the cell has crossing any border. If not, okay. If it crosses, adjust the displacement, and then calculate the speed according with that equation I showed before. Square root of displacement square plus the x displacement square plus y displacement square divided by the time interval. And again, I calculated the magnitude of the force by the square root of the sum of the components square. Now I have both quantities, the speed and the force. After doing that, I have to update the old position of the dictionary of the cell to be used at the next time that I have to change the force. So I put in the old x and the old y, the actual positions, and I plot the values. I think it's kind of complicated, but the code is this with you. You can, if you have questions, please put in the chat that Pedro is helping me with the question there. So let's see the code. Where is the window code? Here. Again, did I save it? Oops. I think I made a mistake. Line 28, let's see, where is line 28? Oh, here, forgot to put the quotes. Again. Oh, I put a dot there. Where did I put a dot? Which line? Ah, here. There is no dot there. Okay, now we have, again. Oh. Where am, which line is that? Ah, 22, thanks. Yes. Again. Fine. Now we have two windows here. Maybe, I don't know why there's a bug with Conversel. Make it run. See, this is speed against force. See, the speed is increasing because the force is increasing. Okay, I will let this running for a while and we move on. After, in a while, I will come back to see what happens with the speed. But I can, well, actually I can show it now. Let's see here. This is what happens. Look, no matter how much you increase the force, because the force is increasing here, according with the Monte Carlo step, this quantity here, but the speed stops to increase. This is a thing that James has showed, I don't remember, yesterday, I think, when he said that the Compusel has a limit of speed. You cannot speed your simulation more than 1 pixel per Monte Carlo step. So this is what happens if with the speed of the cell. It will reach a plateau. It means that the force is growing, but the speed isn't growing anymore. So you reach a speed limit like that. See, you can see the curve here is already bending to reach the final speed limit. Okay. Now we can. How much time I have? I think I went too slow, but anyway, that's it. Let's improve our model to make our cell a little bit more realistic. How? Well, if you see this small move here, you see that you clearly see basically 3 parts of the cell. The nuclei inside the cell, the cytoplasm, and the lamellipodium. Here, you can see the lamellipodium, a very thin stuff protruding and pulling the cell forward. How do we can improve our motion. Okay, we are, where it is, whoops. There are very many models to build a cell. Simple models, actually. The first one, I think, one of the first models to explain this migration mechanism for the cell was proposed by Abercrombie in 1971. And in this model, he proposed that a cell has basically 4 components, which are the nucleus, the actin cortex, or cell membrane, the cytoplasm, and the lamellipod. And the motion occurs according to these steps here. See, the cell starts to organize the actin monomers in polymerization, the actin monomers, and prolongs its tip forward in one direction. Okay. Doing that, he produces adhesion, focal contact of the tip with the substrate where the cell is moving on. And the rear part of the cell is contracted by a myosin action inside the cell. So when this contraction occurs, the cell advances to the right at this picture here. So we have a continuous steps like this, and the cell moves away. Okay? Let's try to do this in a single model. We are going to build a cell which has now 3 components. I will close this project now. Oh, no. Let's start a new one. New project. E42. But now, see, we want the cell have three components: lamellipodium, cytoplasm, and nucleus. Let's call the components as to be short, lamel, cyto, and nucleus. And it's not enough to have a more realistic cell. We have to show the cell having the same structure as a real cell. What does that mean? That means that we have to put the nucleus inside the cytoplasm and the lamellipodium pulling the cell, pulling the cytoplasm without touching the nucleus. So we have to adjust our contact energies for the 3 components to reproduce such a situation, such a resemblance with real cells. Okay, so let me here include the cells. I have the lamel, the cyto, the nucleus. Oops, this one must be corrected. And we want to include at the beginning just these 3 components. But I will include for now already the volume flex, the external local, and the center of mass. Okay. Let's see how we adjust that. At this part of the initializer, I have to build 3 cells, because now each cell, each part of the cell is a different cell: lamel, cyto, and nucleus. Okay, so I have to build here a region with these 3 components. I will do that by where is that for my code? Oh, okay. I have to replicate in this box 3 times, and type in these regions here. 1 cell 120, 120, 129. It's tedious, but, and here it's only the lamel 10. Just aside of it, I will build another one starting 130, 139, oops, 130, here 39. Which is going to be the cyto. And finally, another one here. This way, which will be the nucleus. Okay, let's see how it looks like in the code, in the player. Oh, I forgot to, it's here. Ah, okay, I forgot to give the attributes here. Second part, okay? In the start function, I will design the cell. How do I design the cell? Of course, the 3 parts of the 3 components of the cell must not have the same size. If you look at the movie, the nucleus has not the same size that the cytoplasm. So I will create here a reference volume that I will call cytovolume equals to 300. And now I will say that I will run over the cells. Control copy. And give to each component its right volume. If cell dot type equals to self dot cyto, cell dot target volume equals to cytovol. And do the same test for the other parts. If cell type is lamel, I would say that lamellipodium is about have about 30% of the size of the cytoplasm. And for the nucleus, I would say that it's 20% of the total cell. Okay, and for both, for each one, I will give the same lambda body. In the example here, I made one by one, but here to be faster, I am trying to be quickly. Okay, both has 10 here, and here for the cell, both has the same value. Let's see now if it something is shown here. Oops, see? I forgot something there. Let's start over with one more time. See, this is the initial configuration. See, here I forgot to tell that the initial configuration in the initializer, they have to have size with 10. Let's fix that. It's here, see? Everyone has the same initial size. Save again. Now you have. So here is the cell. Our final cell should be these things. If you put to run here, what's going to happen? They will achieve the target volumes I just put in the start function, and see the green is the cytoplasm, the red is the nucleus, and the blue is the lamellipodium. Okay? So we don't have the cell in the right position. I mean, resembling the real cell. How do you fix that? Of course, if you are doing your simulation, you have to make a kind of sweep of parameter, adjusting here in the contact plugin by hand during the simulation, the energy is to make the cell have the right appearance. But we don't have time for that, so let's fix that. Let me see where this is made here. With this choice of parameters. So I will change here to medium 0, medium lamel 10, medium cyto C2 22, here 100, 5, lamel 11, lamel nucleus is 40, here is 15, and is 0. Okay, so let's go there again. I will start over here. We have this initial. I'm going by step to see what I will increase the size here. And you can see the nucleus entering inside the cell. And the lamellipodium is stick to outside of the site, the cytoplasm, as we want. So you have now a thing that looks more alike to the real cell. Nucleus inside the cytoplasm, rounded by lamellipoid. Okay. Now, as a final thing in this exercise, I will plot a window to see what kind of trajectory the cell will achieve. After we include, I have to include the external potential. Sorry, I forgot that. External potential is here. The question is to make the external potential, the force, randomly change during the cell evolution. To random change orientation, I have to use a new mathematical function, which is, I will import from the Python library random a specific function which gives you a uniform distribution of numbers. Okay, like if you have a discrete situation, this uniform distribution will be the two sides of a coin. If you throw the coin, you have the same probability to have each side equals. If you have a continuous distribution of number, you have a same probability to have any number in this condition, in this continuous distribution, to get a single number. This is a uniform distribution. I am going to use that to make the cell, the force change at its 1000 Monte Carlo stack, because we want to see the trajectory of the cell. Okay, so I will include here in the start function, the situation where, we know that what pulls the cell is the lamellipodium. So we are going to apply force only to lamel part of our cell. Okay, so in this part of the lamel here, I will say that I have, where is the lamel? I will make this here and say that cell lambda vec x equals to start something. Let's put -20. Oh, I don't know, maybe I should do this in the order. Let's do that. I'll do this differently. Let's change the here in the step function. If cell dot type equals self-point dot lamel, I will adjust the cell dot lambda vec x equals to minus, no, I don't need to put the minus here. Let's, oops, like I did in the example, 120 times uniform, a number that I will, which will be picked from the uniform distribution between -0.27 to 0.27. 0.27. And the same for the Y component. In doing that, I will saying that, see, as that number 120 is the same for both components, when I do that, I'm changing only the direction of not the direction, I'm changing the intensity of the component differently for each component. I mean, here I will sort a number, I pick a number from the distribution, which can be anyone, and here I can sort another one from the same distribution, which probably will be different from the first one. So the lambda vectors now, the components are not the same for the cell. That means the cell will not follow a diagonal trajectory over the time. It will not only change the speed, but also the direction of the speed. Okay. So if else, I mean, else, that means that the other types doesn't have zero, doesn't have force applied. Okay. So again, start. Let's see when it moves. I think it's not strong enough. And not being applied, why not? See, the cell isn't moved, but you can see the lamellipodium is changed. That means that the cell has the velocity change in direction, the force change direction. So I don't know why it's not, maybe because it's too small, the intensity. You should have seen these things. This is a small movie here. Why is not? Okay, the code I sent you has the right instructions. I don't know what I forgot here. The Y in lambda back Y.
You're missing the
yes.
percent.
Yes. I'm trying to do it fast and let's see. Maybe I should increase this force. Why is that?
Line 35 should have.
What?
Line 35.
35? Of course, I copied from there. No?
And also you're doing it every Monte Carlo step instead of every so often. You don't have an MCS percent number.
I forgot to test the time. Sure. So the time here, if MCS divided fixing. Let's see. No, now it's right. Because the code was changed too fast, so there was no time to see the cell moving. It's quite slow. The movie is faster because it's a movie, you know, you adjust the speed of frames. Okay, it's working. So if you want the cell to move faster, you can increase the modulus of the force. Okay, let's move on. And the final thing is I think I'm going to just show this part to show the last example. Okay, I want to plot the trajectory of the nucleus. So to plot the trajectory of the nucleus, I have to include the graph window in the start function. Okay, I will not do that to go a little bit faster. In the regular way from the drop-down menu in the CellPython tab, and to include a line at the bottom of the step function here to add a line, a data in the graph. In this data is position of cell position X and Y. Okay, in doing that, you shall have this kind of motion for the cell. See, the cell has a persistent time from here to here, from here for here, here for here, and so on. You can plot for this kind of trajectory the mean square displacement and calculate from this mean square displacement curve the persistent time, for example, as it has been done in the many experimental articles, papers talking about cell migration. Okay, so the code is ready for you as a 423 name in the demo folder. Okay. Now, I was thinking to present this thing here. It was to complicate a little bit more our demo and to show how a 3D cell can be formed. Things get worse because now we have a substrate where the cell is moving on. The cell is a 3D object with 3 components, and these 3 components move over a substrate which can be stimulating a fibronectin layer, for example. Okay. We have now an extra term in this, an extra cell in the cell type in the simulation, which is a substrate type, but this type is frozen, so we don't have to worry a little bit with him. What we're gonna do with this example? Is basically the same as the last one, but now we have Where is the model? Whoops, sorry. I want to show them here. Where's the movie? So, okay, you do the same as that, and then you have this kind of movie like that. Here's the cell, the 3D cell in a box which has periodic boundary conditions in the X and Y direction. We don't need the periodic boundary conditions in the Z direction because the cell is confined in a flat substrate, which is not shown in this movie because I turned off the substrate, and it can be moved as well. The only thing is with this kind of cell, a 3D cell, the adjustment for the energies are much more complicated because now the cell has much more, the cytoplasm has much more contact with the external world, the medium. So the adjustment between this kind of relationship, the such amount of medium, such amount of cytoplasm, and lamellipodium has to be done very carefully. To have this kind of motion here, I have to cheat a little bit and impose a smaller force on the cytoplasm as well. Otherwise, I would take too much time to adjust these parameters. What I have done in a published paper with some people from Porto Alegre and with James. We can see if I can give you a reference if you want. And this is, we can make the cell move without external force. Anyway, the one I want to show you now, because some people talk about flowing cells, is this exercise here. How much time do I have? Should I go every step or just describe it?
You can take, we'll end at
10 minutes?
1:35, yeah. 10 minutes.
Okay, 10 minutes. So I will show the code, and you have the code as well in the demo. So, it's better to do here. So the exercise is the following. It's a bunch of cells, the blue ones there, trying to migrate in a channel. And in this channel, we have a constriction, this part here, and an obstacle in the right side of the channel. So here there are 4 layers of cells. Here we have the constriction, and here the obstacle. Well, at the left side, since we want the cells flowing continuously for this channel, we need to have a source of cells at the left side of the boundary. And at the right side, we're going to include a sink for the cells, which after they faces the obstacle. I mean, after they face the obstacle, the cells will disappear. But the cells will continue flowing because there are a source of cells at the left side. Okay, this is how it looks like the simulation we want to build. Let's go. Let's think about. So to be able to create cells at the left side, we must have some empty space at that region. That empty space will appear after this 4 layer of cells move to the right. So let's say that there is a limit for a specific region on the let's say that the new cells will be created. I will call this X position for this region as an X source, and I will define it like this X position is equals to the half of the cell radius. It's just a position. You can choose anything you want. At the same way, we need to have here position. I think this arrow is a little bit displaced, where the cell must sink, must disappear. So I will find a position here where the cells are very near of the right border of the channel. I will define this position of the X position as X sink, which is the length of the channel, 500, for example, minus 3 times the cell radius. Okay, so it is going to be around here, the position of the sink. When the cell crosses this X, I mean the center, the X component of the center of the mass cross this position, the cell will disappear. Okay, so let's see how that is done. The most challenging stuff here, tedious stuff, is to draw the initial configuration for your simulation, because each line segment, the yellow objects you have in this image, is built by hand in the uniform initializer. Each segment, you have here 1, 2, 3, 4, 5. There's 10 regions of tag regions in the uniform initializer. More the tag to draw the initial cells, and an extra initializer, which is the blob initializer, to build the circular obstacle here. This is very annoying, but luckily I did already. Where is that? Let me show you something here. I think I can move it here just to show you. See, it's a long section of steppable here. First, the uniform, and at the final, the block. Okay, let's continue. Of course, CompuCell has also a tool that you can make use after. Maybe next week we'll talk about it. You can make a draw in any software, any tool like painting or something like that, and draw this setup and transform this drawing in a file that you can use as an initial configuration file. This is much easier. Okay, but since we have not talked about that yet, so I made the draw for you. So let's go on. Okay, for this configuration here, for this simulation, we'll have to use a let's like that, 500 by 104. These 4 are taken into account the width for the walls, the yellow walls in the figure here upstairs in the upper part. Uniform initializer from here, because here in the wizard we cannot load both, only after. We include 2 cell types: the cell itself, the blue ones, and the wall, a wall type to design the boundaries. This wall one will be frozen, of course. The contact we will have to include is the plugins, contact volume local flex, the external potential local flex, center of mass, and a new one, pixel tracker. This pixel tracker plugin allows you to keep track during any Monte Carlo step how which pixel belongs to a specific cell. So you have a list of pixels. If your cell have the ID 100 something, so you can say that pixels, a list of pixels belong to the cell 100 something. Okay? If you don't load this pixel, you cannot say that during the simulation. You cannot find these pixels. So we included that in the simulation here. It is included in the regular way here. It appears like that, like any other plugin, pixel tracker. No arguments at all, like volume, like center of mass. Okay? Let's move. So here's it looks like the code. With adjusted energies, we have all these values here. 12 between cell and medium, 0 with anything that is frozen, and 10 cell. Okay, cell likes more to get to attach to each other than to medium. Okay. And now we have to go to the steppable and see the same thing we did before. We define some variables here to use during the simulation. Here some parameters for the simulation. In the init part of this steppable. In the start part of the steppable, I include the lambda volume and the target volume for the cells, which are not frozen, of course, and the lambda back X for that cell. I mean, only the blue cells are under force, external potential. This is the blue part here. So I test again in here. I think it's better to show here. At each Monte Carlo step, I see if there is empty space. Oops, this is not the one. I forgot. Where is my step now? Okay, I can show here. I don't want to lose time. I define here a position for the source creation of the cells here is cell radius of cell that I have defined it up here. And I run over an X line at X position to see if there is empty space there. See, I'm running at the X position of self RDC, going from the bottom to the upper part of the channel, discounting the walls here. Okay, so I look at that point. I get the point XY and say that this point belongs to a current cell, a variable that I call it current cell. And I test here in the green square, the following square, if the current cell is medium or not. If the cell is medium, okay, then it is an empty space, and I create a new cell using the drop-down menu, which Compu cell has. Let me show you here. Here I have this cell manipulation, create cell. It puts you the snippet to create a cell. So I say that the new cell is the one. I create a new variable. They're saying that the new cell is the cell I just create, and I give the attributes, the usual attributes for the cells to this new cell. Okay, this is how we create a new cell equals to initial ones. Okay, so the next test, I am looking at the other end of the channel to see if any cell has crossed the sync position. Here, I look at the center of mass of the cell and see if the X position is bigger than X sync position, I delete the cell, which also delete the cell is a cell manipulation attribute that you can use from drop-down menu here. Cell, delete cell. Okay? So this is how the steppable go. Now let me see if I can load the simulation here. No, it's this one. I lost my channel simulation. Open, open. Here. Open and play. So it is. So it is running. See? Let me start again to go earlier at the beginning from each Monte Carlo step. See, this is the initial configuration. If I go one by one, you can see the cell start to moving, and after 100 Monte Carlos maybe, it has empty space at that position. Going on, see, a cell appear here because the code has found the empty space. I can go on. Another cells are appearing. So you know how it looks like when the cell appears. Let's release the evolution and see what happens. It's 1 or 2 minutes long. Remember, this is just a toy, no? And showing that you can have such kind of motion of the simulation with tissues, moving with like a wound healing, for example. Experiment. That's a little bit different because here I am imposing external forces on the cell. Some experimental stuff, the cells moving by some external chemoattractants, for example. You can, for example, this obstacle could be a source of some chemical field. The chemical field will diffuse to the other side of the channel, and the cells would be attracted for for the object by chemotaxis, like Pedro is going to show briefly very soon. See, the cells contours the obstacle, and now when the cells start to approach the end part, like here, for example, they will start to disappear. See? It's like there was a sink over there. But in any case, the cells start to being created at the left side of the simulation. Okay, I have passed the time already, but I really want to show this small simulation, this small toy model, to show how we can produce a collective motion with cells, like in tissues, with CompuCell 3D.